Welcome to this explainer. Today, we're decoding the hidden architecture of databases. We're going to take you step by step from raw, chaotic data all the way to incredibly powerful insights. We're basically unpacking the hidden systems that power our modern world, structuring our knowledge just like a software engineer structures information. We'll start with the bare minimum, raw facts, and build our way up to complex extraction queries. Let's get right into it. Think about this for a second. How do we actually make sense of the overwhelming mountain of data we generate every single day? I mean, it's easy to just collect facts, right? But a giant pile of disorganized data is virtually useless. Turning that chaos into structured, meaningful insight requires a highly specialized framework. And well, that is exactly what a database provides. We're going to follow a builder's journey today. We'll start with data versus information, dive right into the anatomy of a database, compare flat file and relational structures, explore database quality control, and finally, learn how to unlock all of that structured data using SQL. Okay, section 1, data versus information. It's time to separate the raw ingredients from the final baked product. Imagine you're holding a standard supermarket receipt. Without any context, the numbers and letters on there are just data. They are raw, totally unprocessed facts. A string of digits like 2.89 or 2.65 means absolutely nothing on its own. It's just noise. But the second it's organized under a heading like price and placed right next to an item name like kiln roast salmon, suddenly it has context. It goes from being random data to meaningful information that we can actually use and understand. So to manage all this newly contextualized information efficiently, we rely on a database management system, or DBMS. Think of it as the ultimate organizational tool for the digital age. A DBMS doesn't just passively hold your data. It empowers you to actively store, access, manipulate, and share it. And crucially, a well-designed DBMS does all of this while avoiding data duplication. That's what keeps our systems fast, efficient, and accurate. Section 2. Anatomy of a database. What's really fascinating here is how we actually build the physical structure to hold our information. In database architecture, precision with terminology is everything. Let's think about a standard table, maybe for an annual sports meet. Every single column is called a field. You can think of a field as a category header assigned to a specific piece of data, like student ID, first name, or age. On the flip side, every single row is a record. A record is a complete collection of those related fields for a specific entity. So in this case, a record would be an individual student's complete profile for the sports meet. Now, here's the absolute most crucial part. Every single table needs a bouncer. We call this the primary key. A primary key is a designated field that ensures no two records are exactly alike, guaranteeing that everyone in the system is uniquely identifiable. For instance, two students might share the exact same first and last name, right? But their student ID will always be different. A primary key is strictly regulated. It cannot ever contain duplicate values, and you literally cannot leave it blank. To keep things perfectly organized within those fields, we assign specific attributes called data types. This tells the database exactly what kind of information to expect. We use text or alphanumeric for things containing letters and numbers like an address. Integer is strictly for whole numbers. Think of a student's roll number. Boolean handles simple binary states like true or false, yes or no. And finally, currency is specifically formatted for, you guessed it, monetary values. Let's move to section 3 and upgrade our architecture to see how this builds into more complex systems. When we compare architectures, moving from a single flat file table to a multi-table relational database fundamentally changes everything. A flat file database stores absolutely everything in one massive, clunky table. The problem? This leads to massive data duplication, which we call data redundancy, and a much higher chance of input errors. A relational database solves this by splitting the data up into multiple hyper-focused tables. It's incredibly efficient, saves a ton of storage space, and ensures your data remains remarkably consistent. But here's the catch. These relational tables can't just float around independently. They need to talk to each other. They're held together by foreign keys, which act as bridges between different sets of information. Let's say you have a student information table and a separate exam results table. The student ID is the primary key in that first table. By placing that exact same student ID field into the second table, it becomes a foreign key. It points straight back to the primary key, seamlessly linking the student's profile to their exam scores without you having to type out their name and address all over again. Moving into section 4, database quality control. We've got our structure, but how do we keep bad data out? The answer is data validation. These are the strict gatekeeping rules that act as quality control, making absolutely sure every piece of data makes sense before it ever enters the database. You've got a presence check to ensure mandatory fields aren't left blank, a range check forces numbers to fall within a logical limit, a length check counts characters to ensure formatting is spot on, and a consistency check compares two pieces of data against each other to make sure they logically align. Let's make this concrete. You wouldn't want someone accidentally typing a letter into a phone number field, right? A type check stops that cold. If you're entering days of the week, a range check restricts the input strictly between 1 and 7. If you enter an expiry date, a consistency check ensures it logically falls after the manufacturing date. No time-traveling products allowed. And for a standard time format, a length check ensures it contains exactly 8 characters. These silent checks are happening in the background of almost literally every app you use. Finally, Section 5, Unlocking Data with SQL. It's time to ask the right questions. We've built, linked, and thoroughly secured our database. To extract the insights we need, we run a query. A query is simply a formalized method of asking your database a highly specific question. It lets you filter through millions of rows of data instantly by setting conditions. You can find exactly the fields or entire records that match what you're looking for. One way to do this is by using a visual interface, often called Query by Example. Let's say we want to filter our annual sports meet database specifically for students playing baseball. You just pop the word baseball into the criteria box, and the software does all the heavy lifting, visually returning only the records that match. But to truly unlock the raw power under the hood of a database, we need to talk about code. If we want to communicate directly with the database itself, we use Structured Query Language, or SQL. It operates on a remarkably logical 3-step recipe. Step 1 is select. This is where you tell the database exactly which fields you want to display. Step 2 is from. This tells the database exactly which table to look inside. And step 3 is where. This is your specific condition. For example, where age is less than 14. Following this simple flow lets you construct incredibly powerful commands that filter massive data sets with pinpoint precision. And SQL allows us to manipulate our results even further. By adding the command order by, we can instruct the database to instantly sort our output, like organizing student ages from oldest to youngest. We can also use aggregate functions. Typing sum, for instance, will instantly add up all the values in a field, like a registration fee, and give you a single total. So whenever you see an SQL query, just break it down logically. What are we selecting? Where is it from? What are the rules? And how do we want it organized? It really makes you stop and think, doesn't it? Every single time you create an account, make a purchase, or post a photo, you're generating raw data. Knowing how highly structured, rigorously validated, and efficiently queried these systems are, how is your own daily digital footprint being cataloged right now? The apps you interact with every day rely entirely on primary keys, foreign keys, and SQL queries to instantly make sense of the noise and turn your everyday actions into meaningful information. And that, right there, is the true power of databases.